Hi, my name is James Coll. Welcome to my ESIP demo titled Google Earth Engine Applications for Painless Parameterization. Today I'm going to demonstrate two applications built in Google Earth Engine that make parameterizing land surface models trivially simple and reproducible. The first, TEAM, or the Temporal Evapotranspiration Aggregation method, is a tool we can use to parameterize evapotranspiration metrics. And the Google Earth Engine Probable Interactive Maximum Precipitation Calculator, which gives us probable maximum precipitation across a host of precipitation remote sensing instruments. If you click on Team, you're greeted with this window. Google Earth Engine provides the data and access patterns Google Earth Engine provides the data and computational power and tools necessary to manipulate literally petabytes of Earth system information from remote sensing satellite. Google Earth Engine provides the data and computational power and tools necessary to manipulate literally petabytes of Earth system data from satellites. Google provides immediate access to the data and computational tools necessary to manipulate literally petabytes of remote sensing information. In addition to that, they've also provided this host of UI tools that you're seeing here to create this interface that allow you to place a wrapper around the JavaScript code of the Google Earth Engine API to make reproducing metrics trivially simple. So in this case, we might want evapotranspiration metrics for land cover types based on some sort of aggregation unit, typically a watershed boundary. We also have a bunch of options to choose from as to which metrics. And to really understand what we're doing with these different metrics, it's worthwhile to take a quick dive into the data science. So we're taking two Modus 8-day products and joining by start time. This gives us total evapotranspiration in kilograms per meter squared per 8 days. Total potential evapotranspiration, average latent heat flux, and the average potential latent heat flux. We're also getting gross primary productivity from the Mode 17 sensor. Finally, we're deriving two metrics, K, a crop coefficient, which is defined as evapotranspiration divided by potential evapotranspiration, and water use efficiency, which is gross primary productivity divided by evapotranspiration. These 8-day products repeat every 8 days in time, and we're taking that and joining land cover from either NLCD or the Modus land cover datasets, depending on this diagram here. So for each of those 8-day products, we need to find a way to cluster those into monthly aggregates. This label is the temporal stat to aggregate. In Google Earth Engine, it's a reducer. In ArcMap, it's cell statistics. And that looks like that. So you get those options, including viewing things as just those raw 8-day tiles. The spatial stat to aggregate is to take each of those monthly images and then, using the zones as defined by the land cover that you choose, give us a metric of choice. In Google Earth Engine, this is a reduce regions call. In ArcMap, this is zonal statistics. And you end up with a monthly series of that metric over the course of the data set. And then finally, there's a table stat to aggregate, which simply takes each particular month and aggregates that out. So if you wanted to know the maximum value for all Januaries or all Februaries, you would be looking for that. So let's go over a quick use case. Let's say you want to run a SWOT model over the city of Tuscaloosa and need to understand what the maximum evapotranspiration is for each of those watersheds. But you're not quite sure what the watershed even is. So we can take the map and just zoom into Tuscaloosa. We actually see that Tuscaloosa is in two watersheds. So there's this one and this one that encompass the major metropolitan area. So let's change our variable to view to evapotranspiration. Let's find that maximum evapotranspiration in each 8-day segment. Let's take the 95th percentile just to kind of crop out some of those outliers at the spatial scale. So again, this would be the 95th percentile of all observations for each zone defined as developed low intensity, developed medium intensity, and so on. And then we'll just pick the table max. So if I click once in one watershed and then once in the other, after you wait for a few minutes, because of course Google is taking this from raw modus all the way through to calculation, we end up with curves that look like this. And while you're sitting here looking at this, you may wonder for yourself, I wonder what's going on with this odd little observation in January. So we can actually, because we chose 24 images to animate, and that's a good value to keep that at, if we click in October 07 of 2008, we'll get the 24 images in front of me, so that'll be 2 years worth of observations. And I just click that. And if you wait for a few seconds, this little window will pop up with the animation pane. If you sit here and wait for another quick second while all of those images load, and you can tell they're loading by that little gray bar disappearing up in the Layers tab. So if we wait a second and everything loads in, we can click play and now gather even more geographic and spatiotemporal context to this data set. So we can see as we page through here, it's got that rise and fall that we might expect from a deciduous location, but for some reason when we loop back around to January, we see that odd quick spike there. And that would be cause for further exploration. If we needed a value to put into a SWOT model based on a month for a given land cover type, based on our particular watershed, we have this reproducible pathway to do so. And now I know I'm running out of time, but the last thing I want to show off really quickly is a probable maximum precipitation calculator. So in the US, we're blessed with a lot of data. Outside of the US, these can sometimes be a lot harder to pick out. So if we wanted to find a given probable maximum precipitation based on a given data set, so iMerge, TRIM, or CHIRPS, we might find a latitude longitude, and I'll just demonstrate how we might compare these two data sources to the Hydrometeorological Design Study Center, the NOAA Atlas 14-point precipitation frequency estimates. If we copy the latitude longitude into that window, we very quickly get a map of that location that we're trying to model, along with our aggregated precipitation data, the frequency factor calculations, depth, duration, and frequency curve data through the time period, and then probable maximum precipitation curves based on the data source. So thank you for watching this. Hopefully you found it useful, and you can see some ways that you might use this framework to show off your data as well. If you have any questions, feel free to email me at jamesmcoll@gmail.com, and make sure you put ESIP demo in the signature. Thanks.